Hello, I'm Paula Chanfreut, and I'm presenting the article A Coalitional MPC Approach to Control of Collaborative Vehicle Platoons. This article has also been written by Twan Keijzer, José Maestre, and Riccardo Ferrari. Let me start with a brief overview of the contents of this presentation. First, I'm going to start with an introduction in which I will introduce the mentioned coalitional approach and its application in platoons. Then I will formulate the MPC problem we consider, and I will go into the main contributions of the paper. Next, I will continue showing our simulation results, and finally we will finish with some conclusions and future research works. So this paper is framed within the field of distributed MPC, distributed model predictive control, and considers in particular its application in vehicles platoons. In particular, we consider a set of vehicles that travel together in a row following a leader, as we illustrate here. These cars can communicate and coordinate their decisions so as to optimize their performance and, among others, avoid collisions. The concept of platoons has been reported to offer promising solutions to pollution and traffic jams, and with increasing interest in connected and autonomous vehicles, distributed control approaches, and in particular MPC, have received a special interest to control such a systems. And this is illustrated here in this bar plot. Here we show the number of results that are found in Google Scholar over the last decade, containing the words distributed control and platoons in blue, and MPC and platoons in red. So in this context, we are especially interested in developing distributed MPC controllers capable of handling switching communication topologies. There are several reasons that drive the study of these aspects within platoons. For instance, the communication links can fail, and this is the approach we consider, as platoons can be large, achieving complete coordination may impose a high communication burden and also require significant coordination efforts. Considering this, we want to design a scalable distributed MPC controller that allows reducing the communication and the coordination burden without compromising the overall performance and the safety guarantees. Following this line of research, this paper studies the application to platoons of the so-called coalitional MPC, which is described in this article. This approach is based on a dynamic adaptation of the level of coordination between a set of MPC agents, as we show in this video. In particular, it proposes to partition dynamically the agents into cooperative groups that are the so-called coalitions or clusters. The main idea behind is that the benefits brought by coordination may be negligible if the agents are weakly coupled, and this coupling can also change in time. So considering this, there's maybe room for reducing the communication and the need for cooperation without decreasing the overall performance. In this respect, we consider that we can change the communication topology among the agents so that only some of them, the ones that are connected, coordinate their decisions. To conclude the introduction, here we summarize the main control goals we consider. We aim at designing a distributed MPC controller based on this coalitional approach so that the vehicles track a reference relative distance. This relative distance is defined as we show here. That is, it is a function of a tuning parameter r and a term that depends on the car's velocity. In addition, we must guarantee safety, meaning collisions avoidance. This must be guaranteed regardless of the switching between communication topologies and therefore of the uncertainties that the cars may have due to the lack of communication. This constraint can be formulated, as we see here, and this will be considered a hard constraint. Moreover, we want to realize these goals in a string-stable manner. String stability is a property that focuses on the propagation of the control decisions along the string of cars. In particular, we want to prevent using increasing control effort as we move along the platoon. The underlying idea is to avoid very large control inputs if the string is very long. The constraint we consider in this paper, this will be a soft constraint, is this one. As we see, it considers the amplification of the increment in velocity over time using absolute values. Finally, the last goal is guaranteeing recursive feasibility. That is, we want to be able to find a solution of the MPC problem at every time step, regardless of the switching between different topologies. And now, let's move to the problem formulation. Each vehicle is modeled by a discrete time state space model as we see here. The state vector concatenates the vehicle's distance, the tracking error, that is the error with respect to the relative distance, the speed, acceleration, and the relative velocity. On the other hand, the input allows implementing a certain acceleration. In particular, in continuous time, the acceleration and input are related as we see here, where this tau is the time constant of the vehicle's drivetrain. Finally, the coupling with the car in front is represented by the variable Wi. Here, we consider the effect of the acceleration and input of the car in front on the state variables of car I. And hence, here we consider the effect on the tracking error. Also, we assume that the vehicles are interconnected by a linear wireless network with bidirectional links. Additionally, we consider multi-hop communication, meaning that the information might be relayed by cars to others farther up or down in the platoon. The links can be enabled or disabled, and thus we impose different communication topologies, as we see here in this example. Symbol lambda denotes the set of enabled links, P lambda is the induced partition, and C refers to the clusters or coalitions. So considering the model we have presented for a single car, the model of each coalition can be simply defined by aggregating the dynamics of all the cars grouped together. In this regard, we define the state vector of the coalition of cluster C as the aggregation of all states of all the cars in the cluster, and similarly for the input vector. Note that now this WC represents the coupling of coalition C with the car in front. For example, for C3, composed of car 4 and 5, WC will be determined by the acceleration and input of the car in front, that is car 3. So using this model, given a partition, the MPC problem that we want to solve in each coalition is shown in this slide. The objective function weights, among others, the tracking error and the increment in the control input for all the cars in the cluster. Likewise, the constraints consider the initial state and the prediction model, some bounds on the control input, the safety constraints, and the string stability constraints. However, it is not straightforward to solve or work with this formulation for multiple reasons. First, this constraint is influenced by the effect of WC, which depends on the current and future decisions of the car preceding cluster C, which is unknown. Second, given the switching between different partitions, we also run into recursive feasibility issues regarding the safety constraint. Note that it may not be possible to satisfy this constraint if the vehicles are not sufficiently spaced or if they approach the preceding car with a high speed or a high acceleration. Third, this constraint is nonlinear, which also complicates the problem solving. So in what follows, considering these issues, we introduce a reformulation of this problem, which under mild assumptions results in a recursively feasible quadratic optimization with linear constraints that also guarantees safety and promotes string stability. This new problem is based on using a scenario-based approach and on reformulating these constraints, as will be explained in what follows. As for the scenario-based approach, this cluster coalition considers a set of realization of the unknown input implemented by the car preceding the coalition. These realizations also include the case in which the car in front brakes abruptly to account for the worst-case situation. As shown here, each of the scenarios leads to different state predictions of the cars in the cluster, whereas the input is computed to be the same in all of them. Considering this, the objective function of the problem of a given coalition, in this case C, is defined as the weighting sum of the corresponding cost in each of the scenarios. In particular, the weight factor PS represents the probability assigned to a scenario S. While this allows dealing with the uncertainties on WC, we still have to consider that at some point, coalition C may be broken into smaller groups, and that all cars must still be able to satisfy the safety constraints. Note that, for example, if a link between two cars is disabled, the follower must start considering different scenarios of the one in front, because there will no longer be communication or coordination. To prepare the cars for such an event, and also prevent recursive feasibility issues, we impose these constraints for all cars I within every coalition C. These constraints impose that car I should keep a more conservative distance, especially when the speed or acceleration of the car in front, I-1, is lower than that of car I. These constraints were derived using the equations defining the model, in particular those that we see here. Using this, we have that if the current distance di satisfies this inequality, then at instant k plus t, the distance di will remain positive even if both car I and I-1 brake implementing the minimum possible input. Instead of using an arbitrary value for t, we consider the time to stand still, represented here as delta. This guarantees that even if the cars brake and come to a complete stop, their distance will still be greater than 0 or equal to 0. Regarding the string stability constraints, this is the relaxed constraint we initially considered for each coalition. As can be seen, it is based on the predicted speed increment over the prediction horizon. This is denoted as dB, as can also be seen in this figure. Using this, we decompose variable dB into two different variables, dB pos, which is positive when the velocity is increasing over the prediction horizon, and 0 otherwise, and dB neg, which is negative when the speed is decreasing, and 0 otherwise. Using this decomposition and the relation between the distance d and the relative velocity delta v, we derive these soft constraints. And here epsilon is a slack variable. These are the constraints that are finally used in the MPC problem involving car I. Essentially, we impose a cost for increasing or decreasing the distance between cars along the prediction horizon based on whether the cars are increasing or decreasing their speed. That said, let's move on to the control algorithm, which summarizes what we have seen so far. At every time instance, all vehicles in each coalition solve a problem of this form. The slack variables and other variables that we defined before are aggregated in variable phi and penalized by this function c. Here we have the scenario-based prediction, the safety and string stability constraints, and the bounds on the inputs. Note that these safety and string stability constraints are formulated as we showed in the previous slide. The coalitions or clusters solve this problem in parallel and thereby get an optimal input sequence UC. From this solution, they get the input that is implemented by all cars I belonging in the clusters. On the other hand, regarding the switching between topologies, in our simulations, we consider periodic revisions of the system partition. In particular, we chose the topologies according to the tracking and relative velocities. That is, when the tracking error is small than a certain threshold and all the cars are driving at approximately the same speed, then we promote a decentralized operation. Otherwise, coordination is promoted by merging the cars into the same coalitions. Now I will show some of the results obtained from the simulations of this algorithm. We considered a platoon of 4 vehicles following a leader, and we used the parameters given in this table. The leader does not communicate with any car in the platoon and implements the input and acceleration that we see in black in this figure. That is, we have a deceleration here and an acceleration here. With different colors and markers, we see the acceleration and input of every car in the platoon. In this regard, this slide shows the evolution of other state components of the vehicles, including the tracking error, which was the one to which we assigned a higher cost. As can be seen, the tracking error remains close to 0 during the entire simulation, in spite of the changes in the number and composition of the coalitions. The error of car 1 reaches higher values as it cannot communicate with the leader, which leads to greater uncertainties. In addition, the effect of the string stability condition is reflected by the fact that there is no overshoot in the vehicle's velocity, and that the vehicle's acceleration does not grow along the platoon as we shown before. Here at the bottom right, we also show the evolution of the network topology, where the green lines indicate the enabled links, and the gray lines are the opposite. As can be seen, a decentralized operation is promoted when the tracking error and the relative velocities are small, reducing the coordination burden and thus the exchange of data between the cars and the coordination effort. Finally, this table shows the cumulative performance cost for the centralized MPC controller, that is, all the vehicles are in a single cluster, and the decentralized controller, that is, each cluster is composed by a single car during the entire simulation. Given this cost and the evolution of the communication topology that we saw before, we can see that the proposed dynamic coalitional approach reached a balance between performance and communication and coordination cost. As concluding comments, this paper has presented an MPC controller for platoons based on the formation of dynamic clusters of cooperative cars. The MPC formulation includes a set of constraints to guarantee safety at all time instants and promote string stability within each of the clusters. Under the considered switching law, these dynamic partitions have been shown to provide a balance between overall performance and the use of communication and computation resources. In future research, we will consider the implementation of this approach in a larger system together with plug-and-play events. Also, we will consider cyber attacks compromising the safety and performance and use this flexibility to enable or disable the communication links to isolate attackers. So that brings us to the end of this presentation. Thank you very much for your attention.